If you celebrate a new accuracy number but never compared it to a dumb majority guess, you might be fooling yourself. We will build simple baselines in Python and line them up against your main model to see who really wins. You probably run experiments and chase higher scores. But sometimes, a tiny trick or a flawed split gives a cleaner looking number than your model deserves. By the end of this video, you will know how to create a set of simple, repeatable baselines in Python. You will also know how to read those baseline scores and decide if your fancy model actually adds value. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Baselines live where your workflow starts. They answer the question, did my model beat chance? In classification and ranking tasks, a baseline is a cheap, interpretable predictor you can compute instantly. Success means your model improves on those simple rules in a way that matters for your users. Fail fast and avoid celebrating hollow wins. At a high level, a baseline is two things. First, a compact rule that produces predictions without training a big model. Second, an evaluation that measures those predictions on a held-out test. For example, always predict the most common label, predict by parity of an ID, rank by a single score, and check how many relevant items appear in the top results. Compute a smooth prior probability and measure log loss, or tune a single threshold on one feature and see whether it generalizes. Each of those is cheap and informative. We will build 5 tiny examples. They ride the same small corpus and the same train and test split. The goal is not production code. It is clarity. Now let us run the first simple check. First, we will test a majority class predictor. This snippet scores a majority class baseline on a small held-out test. It starts by counting labels in the training partition to find the most common class. Then it builds a vector that repeats that class for every example in the test partition. The code then compares those constant predictions to the true labels and computes an accuracy number. The key lines are the count step for the majority label, the construction of the repeated prediction list, and the call to a simple accuracy function that checks fraction correct. There are no free parameters here, so this baseline gives a hard floor you must beat to call your model useful. Next, we will try a deterministic parity rule. This snippet builds a deterministic coin flip style baseline by parity. It uses a field that looks like an identifier or index and applies an even or odd rule to assign classes. The code first computes parity for each example, maps parity to a class label in a deterministic way, and then evaluates accuracy on the held-out test set. The important idea is that this baseline adds structural information from the data schema without learning. Changing which field you use or flipping the parity to class mapping will change results. As a rule of thumb, parity is useful when data has periodic or hashing artifacts you suspect your model might exploit. Next, we will rank items by a single easy score and inspect the top results. This snippet ranks by a simple score and reports precision at top K. It computes a one-dimensional score for each candidate item, sorts the test items by that score in descending order, and then looks at the top K positions for relevance. The code shows how to compute the score, how to sort with stable ordering, and how to measure precision at top K, meaning fraction of relevant items among the highest scoring K. The adjustable parameter K controls how strict you are about the top results. A smaller K focuses on peak quality. A larger K tests broader usefulness. This baseline spotlights whether a single heuristic can capture most of the signal. Next, we will check probabilistic calibration with a trivial prior. This snippet computes log loss for a smooth class prior baseline. It first estimates the class prior from the training data. applies a smoothing term so probabilities never hit zero, and then assigns that same probability vector to every test example. The code then computes log loss, which penalizes confident but wrong probability assignments more than plain accuracy. The smoothing parameter is the main knob. Increase smoothing to make probabilities more uniform and reduce worst-case penalties. Decrease smoothing to reflect stronger confidence in the estimated prior. Log loss gives a sensitive view of whether your model actually learns informative probabilities beyond the global prior. Finally, we will tune one threshold on a single signal and test it. This snippet tunes a one-feature threshold on train and evaluates test accuracy. It iterates over candidate threshold values on the training partition, selects the threshold that maximizes accuracy on train, and then applies that selected threshold to the test split. The code walks through reading the feature, applying a greater than rule, computing train accuracy for each candidate, picking the best, and finally reporting test accuracy. The main parameter is the set of threshold candidates. A wider grid increases the chance of overfitting on train. Cross-validation inside the train fold or a simpler grid reduces that risk. This baseline shows whether a single well-chosen cutoff rival the full model. If you map this toy pipeline to a real project, use the same steps at larger scale. Run the majority baseline, parity rule, one score ranking, smooth prior probability, and a tune single feature rule on the same production split. Log both accuracy and log loss. Time the prediction cost for each baseline. These quick checks reveal whether adding complexity is worth the computation and maintenance. Recap. Baselines are simple predictors you run before celebrating your model. Use them when you want a sanity check or fast failure mode. One caveat: over-tuning baselines to the test split can produce a false sense of security. For a next step, pick one baseline and tune its main knob. For example, if you used the single score ranker, try varying the top K or change the scoring feature. Or, if you used the smoothed prior, sweep the smoothing value and compare log loss and accuracy. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.